Hello. In today's videos, I'm going to describe basically uh, the structure and the content of the YAML file that defines how the DAP analyze the data. Let's see if I enlarge this a bit more. I hope it's readable. I will distribute these files, obviously. The YAML file basically it's the basic configuration file. Remember that when you run the LVMDAP, you are requested yet by three entries. One is a file that you want to analyze in the LVM format as derived from the data reduction. The second is a label that basically is going to be included in the name of all the output files with the different formats, like a DAP file that we described the other day. And finally, this YAML file. The YAML file basically is the core of what are the different options that you can select for fitting the files. When we make a public distribution of the data, we will fix that entry. And remember that in the DAP file, there is an extension, the last extension that contains a fits table with all the information that is in this YAML file, so people can reproduce all the analysis. And obviously, we will need to distribute also all the additional files because this file is calling to other files that are hidden somehow in there that control, for instance, which kind of stellar templates are used or which emission lines are fitted, included in the fitting of the parametric with the parametric procedure and with the non-parametric procedure. So I'm going to go through the different entries. I have added a description to each of these entries, but I'm going to go through all of them. And then if there is if this entry points to another file, apart from the RCP file that I will devote one video to explain the format, the video where I explain how to create it. I will open also that file so you can see the content and I will explain that content. So the first entry is basically the directory where you have installed the DAP file, the DAP package. This is required because in this directory there is a subdirectory named legacy that contains a lot of files that are used for in the fitting process. So when you set this directory, below you will see that there will be entries pointing to a directory that is /. This dot in this particular in this file will be transferred to that entry. So when you see /legacy, it's going to go through to that directory and look for the required files to continue in the fitting. So that's the LVMDAP. It's just the directory where you have installed your own distribution or your own version of the DAP. Then the second important directory is the output path. Is basically the directory where all the output of the analysis will be stored. The third entry, RCP file, it's the location of the file or the file that contains the RCCP templates that are going to be used to analyze the underlying stellar population in the full analysis. Remember the first video in the last loop for the detailed analysis of the stellar population. In this particular case, we are using an RCP template that or library, sorry, that contain 108 templates. And as I told you, I will describe the format of this file in a forthcoming article. Sorry, video. The next entry is very similar. It says RCP NL file. This is the is a similar template as the one that is described before in the similar format. And this is the template used to derive the non-parametric, the non-linear parameters of the stellar population, basically the stellar velocity, the velocity dispersion, and the dust attenuation. So I think I better open again to refresh the memory of the first talk. I'm going to open the scheme included in the article where we show the workflow of the LVM, so you can follow. Let's see if this one. Okay, yeah. So the first this file, the RCCP file, is the one that is used during this decomposition here, the stellar component modeling. Okay, of full stellar modeling. On the contrary, this other one that is a more simple one that contains only 12 templates is the one that is used during this loop where the non-parametric, sorry, this one, where the non-parametric emission lines are analyzed, and where you derive the no, non-parametric emission lines, no, the the non-linear parameters for the stellar population. Sorry for the confusion. So the velocity dispersion, and the dust attenuation. In this first step, it's where it's using this template or this library, and in this other one is where it's used this other library. Okay. Then the next entry is the average instrumental resolution. Sorry, in sigma, in velocity dispersion in angstroms. This is just an initial guess, and it basically the RCCPs may be convolved with this quantity when the resolution of the RCCPs are better than the resolution of the data. That is not the case. We still don't have an RCP library that match with the resolution of around data, and we have to construct that. So this entry is better not to touch by now. We will define different values depending on the differential resolution of the library and the data in the future. The default input format could be that's should be deprecated, and we will remove in next versions. So by now you should left that as RCCP, because it's actually the format that is looking for, and indeed the format is the as I said, the default format is the LVM S frame. If you want to use a different format, remember that you can change that with the input of the LVMDAP conf file, but that entry is we will remove in the future. By now, it's included because if not, the program crashed. But I have to wipe this out. It's not relevant anymore. Now we define. The range, the range of values for the RECIF in the exploration of the non-linear parameters. So in this exploration here is written in velocity, but the code use RECIF. That's totally irrelevant because one is correspond to the other by the usual formula. So we have four entries, sorry, for the RECIF. The guess value, that it's since it's the Milky Way in general and nearby galaxies, is around 0. The offset, that is basically the offset that is used in the brute scan through a minimum and a maximum value that are defined by these two parameters. So this is the guess receive, the delta of the scanning. The scanning is not exactly performing this delta. It's explained in the article. It's randomly around this value. So we have, and since there is a Monte Carlo iteration, you have a pseudo-random exploration of the regime defined by these two entries. And that will be for the receive. In the case of the velocity dispersion in kilometers per second for the stellar population, again, we have a guess value, a minimum and a maximum value. Then this is set to 0 here because I'm just forcing to fix the velocity dispersion that this YAML file is used for analyzing the integrated spectrum and for doing quick tests. But that can be chained. Let's chain that. Let's say that we make a chain between. That's the delta. 2 kilometers per second between 0 and 30. Okay. So if you set that to 0, then it's not scanning through. It's just fixing to the value that you define in the guess. So let's define that to 2. And then how to read that is that the guess velocity dispersion will be 1 kilometer per second. Then it will explore a range between 0 and 30. 30 is also quite low, let's say 50, with a randomly value in a step of around 2 kilometers per second. The third parameter in the three non-linear parameters that define that are applied for the stellar populations is the dust attenuation. Remember again, this is the loop that we are defining, the parameters that define this loop here. Again, there is a guess value that is 0, no dust attenuation, and a step of 0.3 and a range between 0 and 2.5. The more fine, the more thin that are the steps that you put here, the slower that will be the process. In general, the values that we are using span to a much larger velocity dispersion, but not that much because we don't have very huge velocity dispersions in the stellar component that we are analyzing here. So these parameters here define that loop here together with this template and this instrumental differential instrumental resolution. Once we have an RCCP that is matched to the resolution is matched to the data that we have in mind to do that, this should be set to a value near to 0. By now, what it does is taking that, convolving with this, is creating like a smoothing, and then exploring through the range of values and the steps defining by these parameters to define the non-linear the non-linear parameters of the velocity of the stellar component. And in each step, it's decomposing the spectra, masking the emission lines. I will show you later which parameter defines that, decomposing with that templates included in this library. Well, now in here we define a set of emission lines. This file defines a set of emission lines that are masked during this first process. And we define them as strong emission lines. The parameter I define that is emission lines file. Emission lines file include a list of strong lines that are masked during the process of this fitting. Obviously, these lines are shifted to the receive and that is explored in each particular case. And the mask is like 3 fully hat maximums defined by the value of the sigma. So the values around the shifted well length that you define here within three full height maximums of that value will not be taken into account for the fitting of that is used that produce the velocity dispersion, the dust attenuation for the stellar component. How this file look like? This file, I have this open here, and as usual, I have too many files open. This is the full list, and this is the full list, the strong ones. Okay. It looks like this. Okay. So let's increase the font size. It's the well length and an ID. Okay, just that well length and ID, and these lines you don't need to be very refined on the well length definition because it's a band around them that it's going to be masked only during this analysis here. So once you have defined the best fitting, the best decomposition in this simple template, and the best velocity dispersion, and dust attenuation, the program creates a first model of the stellar population that is subtracted to the original data, and from there you start to feed the mission lines, and then you start the second loop that it's where the emission lines are fitted. So again, this is just for masking the strong emission lines in the first fitting, just in the first fitting, when the non-parametric properties of the stellar component are analyzed. The second more relevant list has the same format, it's emission lines file long. This is the list, the complete list of emission lines that are analyzed. Sorry, it's getting a bit slow. I don't know why. Okay, this is the complete list of emission lines that are analyzed. Let me close some things here because I think computer is getting too slow. Too many things open. Okay, it has the same format as before, and this list define the lines that are analyzed in the non-parametric analysis of the mission line, the moment, the weighted moment analysis. So the format is a well length and an ID, and this ID will be automatically, the combination of this ID plus the well length is going to be in the column name that for each different parameters. For instance, for the flags will be flags underscore HI underscore this well length, and then for the error, the E flags, and so on and so on and so on. Okay, so then when this is performed at the very end when you subtract the best fitting of the stellar component and you make the non-parametric analysis. So these are the lines that are analyzed in the non-parametric analysis. If you want to include a different line, you're welcome. You see the list is distributed in the DAP. And if you miss some particular line that you want to be included, please tell me and I will try to do my best. It's just to include another line. Does not create any incompatibility. But the ones that are included here are going to be always included. If not, we create incompatibility. So this line could grow, but will not. I will not remove. I prefer not to remove lines from here. So okay, so this is the format is very simple. Okay. Then we have another file similar to this one, where we define the emission lines file sky. This is the file where we define skylines that basically are going to be masked. Again, they are going to be masked using the and using the instrumental resolution, 3 full height maximums corresponding to the average instrumental resolution that you have defined before, and around these emission lines. And of course, they are skylines. They are not shifted by the receive. The format is very similar to the one that you have seen here. You can put a comment, it's not affecting to the process. So it's exactly the same format that you have that I have shown you before. That basically includes the well length. Let's see if I enlarge that. The well length and an ID. And I prefer to name it like a sky, whatever, just to indicate to the code that this is an skyline. So if you do not include any file here, or you put an empty file, but then no mask will be taken. It's not that complicated. Then we have this parameter, W range. W range is the well length range that is going to be fitted during the full decomposition of the emission lines. Oh, sorry, the composition of the stellar component. So basically, in this loop here, as you can see here for the quick analysis, I cut that to the blue and red arms because the infrared one usually have a lot of residuals from the sky, at least in the previous reductions. And for making a quick inspection, that was why the reason of, the goal of this YAML file. I trim the well range to that particular regime that it's enough and it works pretty fine. An additional mask. This is the max file contain a set of well length range, a minimum well length range, and a maximum well length range per row in the file. It's an ASCII file again. This is the format is very simple. And this range will be masked automatically in the fitting of the stellar component. Why we introduce that? Well, as you may identify, these are the regimes where the different arms match, and we know that we have issues fitting in there. And in general, I think it's a good idea to match those regimes for the analysis of the stellar component. Well, what's next? Config file. This config file, in the future, I think I'm going to use a different format. This is inheritage of Py-3D, and it was well documented in Py-3D. It was the main configuration file that defined how to fit in Py-3D, and it contains entries that are supersede here. It contains 3 lines where you define the receive, the velocity, the velocity dispersion, and the dust attenuation, the gas, the delta, and the minimum and the maximum. Plus, and since they are supersede, these are going to be removed. And then it contains also a set of lines where you define emission line systems that are going to be fitted with Gaussian functions. So basically, this file here controls the parametric fittings of the emission lines that you may remember we do twice, once in the loop where we fit the stellar population, and then we fit the emission lines and we subtract, and when we fit the stellar population again, So this is the PE extensions, PE extension um, in the DAP file. And then we repeat the analysis here that it's in the PM kill KL extensions. No, sorry, this is P, no, it's PM alliance extension is where it's stored the first fitting. And in the PM key EL kinematic, the key case from kinematics is the kinematic is trace on heritage, or it's a guess derived from the result of the non-parametric fitting, and that's why the K came from. Sounds weird, but that's, I guess, it's how it's pronounced. So in both cases, the file that control which lines are fitted is this file. And this file, I said, is very well documented in Py3D, but I intend to be complete here. So I will show you what's how it looks like. As I told you before, there are 3 lines. Okay, this should be a large. This should be a large. Slow. Okay. Okay. So there are 3 lines that you can essentially forget about them because they control the same entries that I told you before, Bresiv, Sigma, and AV that are included already in the YAML file. So the DAP ignore these 3 entries. The most relevant ones are these ones, okay? First, this line, but you need to include them anyway. This number here indicate the number of systems that the program is going to use for fitting the emission lines. A system is a group of emission lines that are nearby in wavelength that they are fitting together. So instead of fitting all the emission lines and fitting individually, we set a certain wavelength range with certain emission lines that are fitted together. This helps a lot when you want to extract the information from weak emission lines, because if you have an adjacent strong emission line and you fix the kinematic parameters to that of the strong emission lines, you can recover better the flux than when you allow a weak emission line to fit with a Gaussian function alone. The reason for that is that the weak emission lines tend to be confused with the background, and well, you can demonstrate that making a very simple simulation, but we know that for a long time ago. So as you see, we have defined 9 systems, and these systems are then described here. So you will see that after these 9, there is 9 rows, and each row have the same format. The first 2 values are the wavelength range that is going to be fitted, and this is shift to the considering the average resif that is defined for the pointing, and this is then there is a file, a configuration file that define the lines that are going to be fitted in here. The rest of the entries are deprecated for in the DAP, so you can forget them. But you have to include them, if not, the program crash. So the most irrelevant thing is the well length and this parameter here. Actually, we have a code that using a set of emission lines create by code and in the memory, not in the file, the same entries that you see here. So maybe in the future this is going to be totally deprecated. I will include a set of lines, and this will generate by itself. The code will generate by itself the required entries. But so far, this is the way that we have defined that. And the advantage of defining by hand is that all these files here um, could include some links between the different lines. Let's see how it looks for instance, the one for H alpha, and in this is one system of the code, the configuration file defined in one system. Let's see again if we enlarge that. Let's go. It's coming slow. Okay. So if you want to learn more about these files, I recommend you to read the documentation of PyPy3D, but actually it's rather simple. There is a first line, ignore all the entries but this one, the second one, that is telling you the number of emission lines that are going to be included in the modeling. And then you have, for each emission line, you have 10 lines. The first is just defining the model that you use, that is a line. There are other models, but they are out of the scope of this video. And then you have the first column is the guess values. The second column is a parameter flag, the 0, 1, indicating if this line is fitted, this parameter is fitted or not, or let fix. The third and fourth is the range. And the last one is a flag indicating if this parameter is fitted freely or if it's linked to the same parameter of other emission line. Let's explain this way. This is H alpha, and the first line is the well length. The well length is fixed, is the well length of H alpha. The second is the flux intensity in the integrated. Okay. The third is width, the sigma of the Gaussian function, and the fourth is the velocity. And then you have minimum and maximum values that are superseded by the entries that you put in the code, the receive range that you put in the code, or by if you are fitting in a loop, it's superseded by the receive of the object that is found for the stellar component. Okay. Then we have a second line. In this case, is nitrogen, and as you can see in the flags, the last entry is -1, means that it's fitted freely, but the parameters, the entries defining the how to fit the velocity dispersion and the velocity is there is a value here set to 1, and the range now are set to 0. When these two parameters, with this parameter here is set to 0, and this is set to a certain value, for example, 1, this should be read that this entry is not fitted, but it's assumed to be the same as the one that you adopted for this emission line. So this is a link between this emission line and this emission line, telling that the velocity dispersion and the velocity are the same to the ones in the H alpha. So it's reducing the number of free parameters, and in general, this increase the quality at the expenses that you assume a certain physical property that is, and they move together. In the case of the second emission line, here we have a second kind of link. For the velocity dispersion and for the velocity, the link is the same. It's 1, so it's attached to the values in here. And when there is 0 here, and this is 0, this means that the link is additive. So it's you have to 0 means you have to add, and this is what you have to add. You add 0, so it's equal to the values in here. But if you set a value here to 1, then it's a multiplicative factor. So how we should read that? This parameter, that is the flux, is linked to the parameter of the second emission line. The second emission line is the strong nitrogen line. And how it is fixed? It's fixed by multiplying the flux in the strong emission line by 0.333. So basically, it's telling that this emission line, if you understand, it's only fitting it's not fitting anything. This emission line is the flux intensity is defined by the strong nitrogen, and the width and the velocity is defined by the first. So basically, that line assumes that you have a scaling of 1/3 of the other. As I told you, this is explained in more detail in the Py3D, but this kind of links between emission lines could be very useful when you have emission lines of different intensity. Anyway, coming back to this configuration file, in here we define 9 systems. Later you will see how it works visually in the screen if I have time. And oh, sorry, I'm speaking too much. And each of these configuration files, since they are distributed, you can check the different links and you can modify at your will and see what happened modifying that. So this is the more complex file within the YAML file. Let's go to the next one. Again, remember that this is for this controls the parametric modeling of the emission lines. Then we have an entry that's clear outputs. This should be set to true. It's a flag that controls if you want to wipe all the files with the label that you define in the when you run the code. And this is to avoid, if, for example, the fitting crash and you have a file that is still open, it may happen that the code try to write below the last row, and to avoid that, the first thing that the code does is you can go to the notebook and see that is to wipe all the files that have the label. Now we have some parameters that are used again in the nonlinear fitting. Maybe I should order the YAML file a bit more, not to confuse the people. This is the well-known range used to fit the velocity and the velocity dispersion, not the dash attenuation. The dash attenuation used the W range, W range that I showed you before. This is using just to define the regime where the velocity and the velocity dispersion is fit. Now you can define a binning, a particular binning. If you want to go faster in this analysis, you can bin the spectral range for this analysis of the velocity and velocity dispersion. But I strongly recommend you to know not to do so. So I set that to 1. But more relevant, you can bin the data in the spectral pixels in the analysis of the dash attenuation. See, the dash attenuation basically is derived by the shape, the mismatch of the shape. Then to fit the several thousands of pixels that we have in the data is not relevant, and it can become very slow. This is like creating a spectrum with a very low resolution, and this way you fit the dash attenuation much faster. Okay, mask file. This is a superset, but it has to be included here. It was another way to define bands, but the bands that move with the recessive. Just in this may be useful in the case that you are analyzing data, not like the LVM, that you analyze this data where you have holes in a certain Weller range that depends on the receipt, but that's you can ignore, just set to 0 to none, and that's all. And now there are some flags for making the fitting faster somehow, like for example, ignore gas. This is a flag where if you set that to true, it is going to fit only the stellar component. That's not pretty useful for the local volume mapper, but if we want to make tests, particularly for fitting stellar components, then it's sometimes good to say set to true and ignore that. Single gas fit. You can iterate the fitting of the emission lines several times until converge. That's in a sense, this is not. It was a test I did. It's not improving too much the results. So I set that to true, and it's going to run the fitting only once through all the Monte Carlo iterations. Um, then we have a sigma gas is the guess of the velocity dispersion in astrons, the instrumental velocity dispersion, an average guess. This is used only as the first guess of the velocity dispersion for the non-parametric analysis of the emission lines. But after the first loop, this is rewritten by the result of the first loop. So this is just an initial guess to define the kernel that is used for the weighting of weighting moment of the non-parametric derivation of the emission line properties. This other parameter, flux scale org, it's in general is pretty useless. Is basically just for plotting, controls the minimum flux and maximum flux in the output plotting. If you set to -1 and 1, then it's going to automatically decide the optimal ones. But if you want to make tests and you want to focus on a particular well-end range and a particular flux intensity range, then you may require to set these values, not to need to zoom in the output. Okay. Single RCP. Single RCP, that's an interesting feature, is set to false when you want to make the full decomposition of the stellar component in the using the RCP template. If you set to true, instead of making a full decomposition, it's going to look for only the one single spectra in the RCP template that match better with the shared spectra. So instead of making the composition, it looks for the single spectra, single template that match with the shared spectrum. This could be valid or useful when you know already that you have a very low signal to noise in the continuum, or if you want to identify the stars in the field, um, uh, which is the star in the RCP template that match better with that particular star. So kind of tagging for the stellar components. Of course, for the full analysis of the LVM, this should be set to false. Do plots is a flag that is should be 0 or 1. That when it's 1 is going to create the output summary plots, like output summary plots, like for instance this this plot. Let's see if it's open, or I may have it opened, but it's not shown. Why? Why? Where it is? Okay, like this plot, for instance. This summary plot of the fitting of integrated spectrum. Okay, if you set that to 0, those plots are not created. In general, it's good to have them to have a visual inspection of the fitting. Then we have some two parameters that are usually adopted for making tests. That one is NY range. Range is the range of fibers in the RCC file that are going to be fitted. If they are not set, the full file is fitted. But imagine that you want to make some test and you want to use, for example, the first 100 spectra. So you set that to 0 and 100, or the first 10, just to make tests that on the configuration file or whatever. No, this is useful just for testing. The same works for NX range. In this case, the RSCP file is trimmed to the pixels corresponding to this Wellen range. This could be dangerous if you include emission lines that are out of this Wellen range in analysis. It is going to crash because you're going to we're going to look for files for emission lines that are out of the Wellen range, and then the code will crash. But again, if you are interested in fitting one particular Wellen range, or you want to make a very, very fast analysis for testing, testing the code, testing modifications in the YAML file or whatever, it may be useful. In general, should not be defined. The output of the plot figures, this should be near to this entry here, PDF or PNG, not very complicated, outplot format. Another interesting feature, if this is a flag named only integrated, if you set to true, is remember that when I explained how the code works in the notebook, first the code runs through all the steps just for the integrated spectrum. Okay, if you set that to true, the code stops there and it just analyze the integrated spectrum. If you set to false, then it's run through all the RCPs or through the range that you have defined here. Okay, as I explained the first day, the code, or the second day, I don't know, the code basically look automatically for the receive matching the H alpha and nitrogen lines detected in the spectra and making a scan, a brute scan, pseudo cross correlation with the expected locations for these emission lines. And this is controlled by the parameters that are explained here. If you set this auto receive to true, then the receive value, the gas receive value that was described before, is ignored, and it's going to look for within a range defined by this minimum receive, maximum receive, and in a pseudo random step that on average is defined by this delta coming from delta. Is going to explore which is the receive of the average spectra or the integrated spectra in the field of view. This is useful, for instance, when we are exploring the Milky Way, then we know that with the same configuration file, we can run through all the spectra without any problems, setting that to false and defining the gas receive to almost zero. But then you jump to the LMC or SMC, and since we are still using a single file so far, then this or some of the galaxies in the local group, then you require to making an automatic receive. I'm not totally sure if at the end this is going to be working in this way. Most probably what is going to happen is that we're going to have copies of these files, this YAML file, that are going to be useful for certain regions. And then instead of letting the program, because this may create problems if the signal to noise is low, but so far it works pretty well. But we know that at the edges of the Magellanian clouds, we are finding problems. So maybe in the future this will set to false, and the guess receive will be written depending on the position in the sky of the frame that is going to be analyzed. Anyway, it's included, and so far it's working reasonably well. For this, there is another parameters that control this automatic search of the receive. This is in here, this auto Z background is set to true. In this way, what is happening is that the continuum spectra is subtracted It's first derive, that's what control this parameter, and second subtract it. Using instead of making a modeling of the underlying stellar population and so on, it makes an analysis similar to the one that we adopted for the data reduction pipeline for deriving the continuum component of the sky spectra. It's exactly the same routine or an old version of that routine, and that we developed like 1.5 years ago, and it works pretty well for making this extraction. When you make this extraction, then you have just the nitrogen and H alpha lines, and it's the contrast is higher, and the autoresif works better. Skyhack, this should be set to false with the new version of data reduction. This was a hack for subtracting the sky using this routine and the sky information in the LVMS frame, and that was developed when the sky subtraction was not that good in the data reduction process, and in the previous analysis of the all analysis of the data, we set that to true, but this should be set to false hereafter. Okay. And finally, these are the two last parameters. One is the signal to noise cut, SN cut, and signal to noise cut integrated. SN cut basically controls the signal to noise level in the continuum at the average wavelength of the wavelength range analyzed, above which the analysis perform a full decomposition of the stellar component. If the signal to noise is below that cut, the program, what it does is to make a single analysis. It look just for one star that match roughly the shape of the stellar component, because below that signal to noise, you have signal to noise of 20, you cannot make the composition of 108 templates. And actually, the only information that you may get is which star is more similar to this continuum, and that's all. In this case, the errors are set to 0. So when in the coefficients of the decompositions you have all the values with zeros and only one value with 1, this means that it's not making a decomposition, it's just making a single matching. And that's because the signal to noise is below this threshold. And finally, this signal to noise cut integer is basically the cut applied to the integrated spectra for making the analysis of the integrated spectra. And as you can see, it's pretty low because this applies only to the continuum, and we want to derive also the emission lines. So that's, I think that at a certain moment this is going to disappear from the configuration file. So as usual, this video is taking too much time, but I think this information was very important, and you can see the video in 2 or 3 blocks if you don't have 1 hour for seeing it. I hope this information will be useful to all of you.